So good morning one and all. Now I would like to give introduction about our speaker for the session 2, Dr. Sridhar Swaminathan. Welcome sir. Dr. Sridhar Swaminathan is working as Assistant Professor, Department of CSE, Bennett University. He is having specialization in computer vision. He has completed his PhD in CS from Bharati Dasan University, Tricky, if I'm not wrong. Okay, so now over to you, sir. Please take the charge.
Thank you, madam. So I'm very happy to be here. Good morning to all.
Welcome, sir.
Yeah, madam. So thanks to
Welcome,
the
sir.
management of KIET group of institutions and all the organizing committee. So looking at the topics discussed in the whole FDP, I'm really fascinated because all of them are actually the current state of the art. None of them is like just machine learning or deep learning. They are like giving things which are currently relevant. So I'm very happy to see that whole schedule on board with a lot of really like hot content. So let me start my presentation. This will be actually a hands-on session, but let me give a quick overview about what is transfer learning and how we can actually use the transfer learning for computer vision applications. Okay, so this will be a like little bit of theory for 15 or 20 minutes, then a hands-on, and I want this session to be very interactive. Please don't do like I'll be presenting and then you'll be like just listening. So we should not like restrict with only one-way communication. Okay, whatever doubts you have, please let me know. There is no like discrimination in the type of question. You can have any kind of question. There is nothing like silly question or advanced question. Okay, so if you have doubts in your mind, then you have to get rid of it as soon as possible because you cannot live with the doubts. So doubt is like a luggage. You cannot carry that same luggage for a long time, you know. So whatever doubts you have, please feel free. Please don't think like it is a like really good question or a bad question. Any question is a good question. Okay, so the thing is like there is some phenomena called transfer learning. We know deep learning, we know machine learning. Now what the hell is like transfer learning? What we want to transfer? Okay, and this transfer learning is some kind of strategy that we want to use. We want to use it for computer vision. Computer vision means we want to use applications in images and videos. So that means that we are going to deal with a like model which deals with computer vision. So we'll be dealing with the convolutional neural network. I think previously you had that session, and we are going to use the transfer learning of convolutional neural network for doing some task. Okay, and using the state-of-the-art TensorFlow models. TensorFlow is actually the language or the API for deep learning, and we'll see like all these things one by one. Now the thing is like if you want to develop any application, you don't need to train a model from scratch. Especially if you are working with computer vision, you want to develop maybe a classification model for a new data set. You don't need to train a model from scratch. The thing is, you can actually use a model which is already trained for some other task, and then you just transfer the knowledge which was like there for the some other task or some other data set, and you try to transfer it for the new data set. Okay, for example, if I want to classify between aliens versus human, maybe I have like only few number of pictures. There is not like too much varieties of pictures are there. If I start training with the model from the scratch, what will actually happen? If the data is limited, then the model will most likely to overfit. You know what is overfitting? Like model will do really well in the training set, but perform very poorly or badly in the testing set, unknown data set. So that will obviously happen if your model is trained with a lesser number of data with a lesser number of variation. Okay. So for that, what we are going to do, we are going to take a brain which is already trained for some other task, and we are going to use this brain for doing a new task, aliens versus human. Okay, and the thing is like you don't need to train the model from the scratch. You don't need to train the model with the random weights, where you can take a trained model, trained weights, and then use it for some other task. Okay, so that is something that we can relate in our real life also. uh, so this is called a transfer learning. We try to transfer the learning which is done in one data set or one task, and we want to transfer it to another data set or other task. Okay, why I mean by like task? Sometime you will be like using the model which was trained for the image classification, and you will be using this model for doing the object detection. Both are different tasks, but there is only one thing common, which is the images. Okay, so transfer learning is like you try to transfer the learning. It is not like you try to like transfer the data. You are trying to transfer the learning of the model. Learning of the model is nothing but the trained weights. Okay, and this is what we actually transfer. So obvious example for transfer learning is you know how to program in Java, C++. When you first encounter Python, you're not going to deal with the Python with a like empty mind. You already have a knowledge about the programming languages. So your mind is already trained for the Python and Java and C++. You are going to use that knowledge. You are going to use that learning to learn a new language, which is the Python. And you would have learned the Python within like maybe few weeks, because your mind is actually not an empty mind. Your mind is already having a learning which was gained during the learning of C++ and Java. Okay. So if you know how to ride a bicycle, it is very easy to ride a bike, because you know like there are fundamental things which are common across this. Okay. So the thing is, the transfer learning scenario is actually very much useful. That will reduce the like resources that you are going to use for training the new model. You don't need to train too much. Similarly, even if you are training with a lesser number of data, the transfer learning is actually helping you to overcome the overfitting problem. So the model will not obviously overfit. The model will actually try to generalize if you are using the transfer learning. Okay. So there are too many things we have to like consider while doing the transfer learning. How much previous knowledge has to be used in the new domain? That is like one thing. How much is the similarity between one source data set and the destination data set? That is like other thing. And how much tuning that we have to do, whether you have to like change the old model, or we don't need to change the old model, or we need to like fine tune the old model. All these things are actually matters. Okay. So we'll see it in the practical scenario also where it can be used. So the thing is, this transfer learning can be applied in other domain also. It is not just for CNN and computer vision. It can be applied for natural language processing. It can be applied for any other task. Okay, maybe in the signal processing. In the audio also you can use it. Okay. In the NLP, I'll give an obvious situation. For example, if you are training the model for dealing with sentiment classification in general, okay, just like it is not related to any domain, but you have a sentiment classification model for a like general comments. Whatever the comments you give, it will actually do the sentiment classification. If you want to use that model for a specific domain, for example, maybe in the movie domain, you don't need to train a new model. What you can do, you can just take a general model which is applied in the general scenario, and you try to fine tune it for the new domain, which is the movies. Okay. And this particular new domain will have like a limited vocabulary, limited number of situations, limited number of features, and your model will be trained for this particular new domain. Okay. So the transfer learning ideology can be applied in the computer vision, it can be applied in the natural language processing, it can be applied everywhere. Okay. And where we are going to apply, we are going to apply it on neural networks. So the transfer learning means we are going to take a trained neural network and we are going to use that neural network for some other task. Okay. It is like taking the brain of something and then fitting into some other's head and then asking them to do a different task. It is more like a brain transplant. Okay. Transfer learning is like a brain transplant. Nice, right? So this is how it happens. So usually if you want to maybe train the model for this kind of like a domain based data, like classification of uh, accessories like shoes and dress, coat, etc. You don't need to train a model from the scratch for this new class. What you can do, you can just take a model which was trained on the like general domain. So there are like a lot of state-of-the-art model trained for the ImageNet dataset. Now this ImageNet dataset is actually one of the largest datasets with like more than 1 million images and 1,000 classes. So there are like 1,000 classes and 1 million images. And the size of the dataset is actually growing too much yearly. So what you do, you try to like train a model from scratch for the ImageNet dataset. Not, I mean, like people have already trained the model from the scratch for the ImageNet dataset, and they have a network trained for 1,000 classes. So what do? You just take the brain, and the thing is, like, you don't need the last layer. The last layer is having a knowledge for these 1,000 classes. We don't need that. So what we do? We just remove it. And then for the new data set, you just find how many number of classes are there. If it is 5 classes, then you add a layer with a dense of 5 layer with a softmax activation function. Then you have a new model, totally new model. And this entire model will be having the already pre-trained weights. Okay. And this new layer will have a randomly initialized weights. The layer that you are adding, these connections will be randomly initialized weights. Now the thing is, you are going to use this particular base model for doing a classification of this 5-class classification for this new domain. Now the question is, can we train these weights also? Can we do some fine tuning? Of course, there are many scenarios where you can try to fine tune the base model. Sometimes you can freeze the entire base model. Sometimes you don't want to train the base model. Okay. So when doing the transfer learning, few things that you have to keep it in the mind. You don't need the last layer of your base model because that is actually the classification layer for some other data set. And you need to add a new layer. And you may be thinking do I add just one layer for the new class, or can I add maybe one more layer in between the last layer and the classification layer? Can I add like that? Yes, of course. So imagine that this is the last layer of the base model, and this is the number of classes. You can directly connect, or you can just learn one more layer, two more layer, and then finally you can just connect. And the thing is, the newly added layers will have a random weights, and you need to train that model for this random weight. So what you will do? You will decide whether to freeze this entire model, or whether to freeze maybe half of the model, or maybe to freeze where you don't freeze, you just train the entire model. Okay, so this particular process is called fine tuning. Fine tuning is you are trying to tune the model in a very minute granular way. You're not changing the base model too much. You're going to fine tune it. Okay. You don't need too much of rigorous training here. You just need only fine tuning here. Okay. So this is training, but this is fine tuning. You don't call it training. You will call it fine tuning. Or sometimes people call it retraining. Retraining means you are training it again. Okay. So if you are working in the same domain, maybe in the similar data set, you are going to call it retraining because you are doing the training again. If you are going to use it for transfer learning, most of the time we are going to use the word fine tuning. We fine tune the model. Okay. So there are different scenarios where you try to do this stuff. Okay. So if you have small data, what do you mean by small data? Small data is not like a small image or like a large image. It has nothing to do with the size of the image. Small data means the number of samples. If your data set contains very less number of samples, what do? You take that base model, freeze that entire base model. What do you mean by freezing? When you train the model again for the new data set, you are not going to update these weights. That is called freezing. Okay. And you are going to train only this part because that is a layer that you added, a new layer that you added. Okay. So this is called freezing the base model and then training. And this will happen if you have a small data. Now the question is why, if you have small data, why you are actually freezing the base model? Why you are not training the entire model? Anyone? So I don't think a chat box is enabled. So maybe if you have any group, WhatsApp group or something, then please post your queries, and I would request the organizers to maybe.
Sridhar sir, we will take query and last 10 minutes of this session.
Okay, sir. I think we can take the queries in the last 10 minutes. But maybe
yes, sir.
Before I start the hands-on, also I will give maybe some time for
Actually, chat sir is not open
yeah,
for
yeah.
Outside.
Yeah. So okay, I get it. Okay, no problem. Okay. I think Somebody raise the hand because they maybe I think know the answer. So let me try to like reveal it for you. The thing is like if you have small data, then you know that you are most likely to like overfit the model. You know why? Because with less data, with less evidence, we try to like train the entire model, and you don't have enough confidence to train the entire model because you have less data. So you don't want to like maybe change the behavior of the base model, because the base model was actually trained for the like big data. And the knowledge which is there in the base model is actually for the big data, and that will not overfit. So what we'll do, we try to freeze the base model and we try to like train only the layer which we added just now. Okay. And if you have mid-size data means like it is in the number of samples are actually in the thousands. It is not in the lakhs. It is not in the hundreds. It is in the thousands. And again, maybe looking at the scale of the data, it is not too big. Okay. So what you do, maybe you try to freeze half of the network and then try to train rest of the half. And you have to like understand one more thing, that you try to freeze only the first half. The freezing actually starts from here. We don't want to retrain this part. We try to retrain only the part from the last layer. You know why? Because these base layers in the CNN model, they try to learn very basic features. Okay, these layers in the CNN model, they try to learn features like what do you call CNN feature extraction. So the first layer will try to extract the small edges. Yeah. The first layer will try to like extract the edges, and the second layer will try to extract the curvature, and the third layer will try to extract the like much more higher level stuff. So the thing is, these base layers, they try to extract basic features like edges and then curvatures and all. So the thing is, these features are actually common across all the data sets. In every computer vision data set, these basic features like edges and curvatures, these are all common across all the data sets. Okay, but these higher level layers, they try to extract the like cat head and then like maybe the car, or they try to detect the like a wheel of the car, something like that. So if you are training maybe the model for a totally new domain, we don't need like features like a car and then head of the cat, maybe wheel of the car, headlight of the car. We don't need such a high level features. So we can actually retrain it. We don't need this. But these basic features like the edges and then the curvatures, they are common across all these different domains. Okay. So that's why we try to freeze the base layer, because they extract the basic features, and we try to retrain the further layers which are actually near your classification layer. So the training will actually start from the last layer. So what I mean by like training the half, freezing the rest of the half. It is not like if the model is like maybe 20 layer, it is not like I'm freezing the 10 and then I'm training the rest of the 10. It's not like exactly the middle. Maybe it is like 8 and 12, or maybe it is 12 and 8, somewhere in the middle. Okay. Again, it depends upon how much you want to train in the model. And if you have enough data, you have like a big data with you and you want to use a pre-trained model. So one more thing is, if you have enough data, sometimes you don't need a transfer learning also, because you can train a model from the scratch for the enough data. And if you are using the transfer learning, you can unfreeze the entire model, base model plus the layers that you added just now. You can just train the whole model like rigorously. Okay. So this is the scenario called transfer learning, and this has a lot of cool applications. If you have base model for the image classification, you can actually apply it for object detection. You can apply it for image segmentation. You can apply it for any other higher level like visual, what do you call, visual relationship detection, VRD. If they have image with the 2 or 3 objects, you try to find the visual relationship, like cat sitting table. Cat is actually sitting on a table, so you'll find like cat is there, action is sitting, and then there is a table. Object detection is like just detecting the cat table, but the visual relationship detection will actually find the relationship between the 2 objects. So it will find like what kind of interaction is happening. If the cat is actually sitting under the table, then the model will say like cat under table. It will not say like sitting table. Sitting means like it is sitting on top of the table. So those kind of visual relationship will be like very helpful. And those models which are actually trained for visual relationship detection, they use a pre-trained model which is actually there for image classification. So for most of the tasks in the computer vision, you try to take the models which are trained for the ImageNet competition. Okay, so only those are the models which are very, very useful for transfer learning. Using this model, which is done for image classification, using this model, you can do a transfer learning for image classification, you can do for object detection, you can do for image segmentation, you can do for visual relationship detection. You can use it for anything, okay? Let me give you like maybe a few more examples. There is an object detection model called the YOLO version 3 or something. So these kind of models, they try to use a base model which is actually from the, what do you call, image classification. Okay, so let's take the architecture of the faster RCNN. There is a faster RCNN model which is very famous for object detection. So what they do, they take an image, extract the basic features from the VGG16. VGG16 is actually a pre-trained model which was trained for ImageNet dataset. And using the VGG16, you try to get the visual features, and from there you try to train the object detection model. So this base model will actually become a learner, will actually become a feature extractor for your higher level task. If you want to do maybe object detection or anything, you can actually use it. So most of the time people actually use the models which are actually trained for ImageNet dataset. Okay, so let us see all the models which are there in the TensorFlow for the ImageNet dataset. So TensorFlow, I guess you all know the package, which is actually very much famous for doing the deep learning implementation. Okay, I think this will be useful. So there is like one more related package called Keras, which has like a lot of models like exception, VGG16, VGG19, VGG16 and 19 are very famous. ResNet 50, ResNet 101, all these are like different models which are proposed for the ImageNet classification. Okay, if you want to use one of these models, you just need to call this line, it will directly download it. Okay, so today I'll give you like two examples or two notebooks for you. Okay, I think this particular notebook is already shared publicly. Yeah. So maybe after the demonstration, I will share this particular link and the data with you. Okay. So this platform is called Google Collab, where you can actually upload your Python notebook and then run the model for free. So we need to collect our Collab server to the like Google Compute Engine. So it is connecting to the Google's backend engine. It will automatically allocate some GPU memory and RAM and then the hard disk space. Okay. Great. So in this transfer learning model, what we are going to do, we are going to like take a pre-trained model. We are going to create a small data set. And in that small data set, we are going to keep two classes, cat and dog. For cats, we are going to have some number of samples. And then for dogs also, we are going to keep some number of samples. And we are going to train the model, a CNN model based on the ImageNet data set. We are going to train it for this new data set, cats versus dog. Okay. So before we actually start, let me give a sneak peek of how the data set will actually look like. All right, if you want to actually download this data set, I'll give you one more way. So in the GitHub you just search for the user account called Maja Matrix. It is the name of my YouTube channel where I try to run the channel for like all these things in Tamil. I used to like teach it in the Tamil language. Okay. So there you can find DCNN and then there is a data. Okay. And I am actually using the notebook which is there in the CNN transfer learning. So within the data, there is a folder.
Sridhar sir, voice is lacking.
Voice is lacking, sir? Is it clear now or still? Is it clear now? Is it from my side or?
No, sir, lacking. Your voice is lacking.
Okay. So maybe let me switch off my camera and then try to. Yeah. What about now, sir?
Okay, sir.
Okay, sir. I think my streaming video is also on, and then this screen is also in the streaming. Okay. All right. So there is this particular page. You can go there, and then you can find D_CNN. There is a folder called data. Within that, there is a train, and within that train, there is a folder called cat. Within the cat, we have two images of like cats. There is like one cat, and there is another cat. And the beauty is like all these cat images are actually in different sizes. And if you are going to give this model data to the model, then the size has to be like resized. Okay. And it is not possible to manually resize them. So we try to like do it automatically. So we keep like two folders within the train, and then within the validation, under the folders, you just keep some images. Okay. And what I'm going to do, I'm going to like upload that particular folder as a zip folder here. And later I'll share this data.rar, which is actually the zip version of your this particular. So it will take a while to actually upload. Yeah, it is uploaded now. All right. Now we are going to use this particular data set for training a new model for cat versus dog. So now let me like import all the necessary libraries. We are going to use matplotlib, and then inline means like you are going to display the plotting within the matplotlib. It is not going to pop up anything. NumPy as an NP for numerical computation. There is pandas as PD. Pandas is a very famous package for doing the data pre-processing and etc. So there is a package called Keras, which is again written using the TensorFlow. The Keras actually provides a high-level way of writing the deep learning code. You can write a big deep learning model with a simple lines of code. We can just train it using few lines of code. Okay. So that is there. From Keras.preprocessing, we are pre-processing like getting one package called image data generator. Now this package will help you to like generate the images from the folder. So you don't need to read the images, you don't need to resize the images. This will help you to read the images and then create the data set. So from Keras.model, we are importing the model, means we are going to use a model API for creating the model. From the layer, we are going to import input, flatten, dense. We need this because the model actually needs input, and whatever output we are getting from the pre-trained CNN model like VGG16 or ResNet or whatever it is, we need to flatten the output. Sometimes the output of the model, sometimes this will be as a 3D matrix. This will be something like a 2 by 2 by 128, something like that. So you cannot like directly connect a dense layer with this particular 3D volume of activation. So you need to like flatten this 3D volume into a single dimensional vector. Then only you can add a dense layer for your final classification. Okay. So we have this particular flatten layer. which is going to flatten the output of the base model. And finally, there is a dense layer. This is for your new data set. So here we have like callback for saving the model. You try to do some checkpoint. Now from the keras.application, we are importing the Vgg16. Vgg16 is actually from the visual graphics group of Oxford University. There is a session layer neural network which was very, very famous, which is used to be like a famous base model for many computer vision tasks. For object detection and image classification, they try to use it. And keras.preprocessing, we are importing again image, again preprocess input. So every model, every like a model in the literature, they use different types of preprocessing. So we need to actually import that particular preprocessing because there is no standard preprocessing method. So sometimes people will try to normalize the image, sometimes people will try to whiten the image. So those preprocessing will be different for different models. So that also you try to import it. All right. So we try to import these packages, and all these packages are already built in your Google Collab platform. Okay. Now I'm going to unrar this particular zip folder. So what I'm going to do, I'm going to unzip it. So it is creating the folder called data, and then within that you are going to extract all these things. So there is a train, there is a validation. So train will be for training, validation will be for testing, and then this is 2 images for just to like play with the model in the prediction. Okay. So now I extracted the images. So here I'm going to download the model, download the Vgg16 model, and that will be the Vgg16 convolution. Now the weights equal to ImageNet. We are telling the model that download the weights of the ImageNet dataset. So the weight that we are going to use for this particular model is going to be for that ImageNet dataset. So it means the number of classes will be 1000. But we are saying that include top equal to false because we don't need the last layer of your base model. The last layer was actually doing the classification. We don't want that. We actually want only the feature extraction layer that is before the last layer. So that's why we actually put include top equal to false. Now you can see that a model will be actually downloaded here and the weights will be downloaded. You can see that storage and then TensorFlow, Keras application. So VGG, weights, DF, dimension ordering, TF kernel, no top, .h5. Now this h5 is actually the file format for storing large number of like floating point numbers or large matrices. It's called a hierarchical data format, HDF5. So now if you see the summary of the VGG model, you will see that this VGG16 model has like 16 layers. And the last layer is actually giving an activation of 512. Now the model has like a total number of parameters, 14 million, and the number of trainable parameters are 14 million. And number of non-trainable parameters are actually 0. Means the entire model can be now trained, retrained. But we don't want that. We actually want to freeze the entire base model. We want to train only the new like layers. So what we'll do, we actually try to like iterate the layers. Model.layers, we try to take each layer. Layer.trainable equal to false. If you keep that, then this entire model will actually become frozen. And if you are going to use this Vgg 16.con anywhere after this, you cannot actually train the weights of the base model. So now after setting this, if you see the summary of the model, again the weights will be same. But here the trainable parameters will become 0 and the non-trainable parameters will actually become the model, entire model itself. Again, you may be thinking like, okay, if I want to actually maybe freeze half of the network, then how I can? So let's see like how we can actually get the layers. Now these layers are actually like here as something. For example, if I want to like freeze only the half of the layers, so you can just see that this is a kind of list of something. So let me find the length of the list, 19. Okay, so I will say like layer size equal to 19, and I want to freeze maybe the half of the layers. So how I can do? So I can say that there is something like count equal to maybe 0, and for each iteration we try to like count plus 1 equal to, sorry, plus equal to 1. We are trying to add the counter. If count is actually lesser than or equal to the ls divided by 2, means half of the network, then you try to like keep it as a false. So what I will do now, I think since it is already frozen, I need to again freeze it. Okay. Oh, less than or equal to. Oh, I think. Length will be 18. Okay, I think. Oh, my bad, my bad. I think I need to reload the model again. My bad. Yeah, so now it is like a trainable is all parameters. Now if I try to freeze only the half, you can see that there is like a trainable parameter up to this, and then there is non-trainable parameter up to this. So you can see that most of your parameters are actually coming from the rest of the half only. Okay. So up to 10 layer I have frozen, and the rest of the layers I am just going to train it. Okay. So this is how you can actually do the freezing of half of the network, or maybe like not freezing the half. I'll try to like redo all the things. I will try to like. So here in this lab, we can actually play with the model. We'll see like what happens if the model is actually frozen entirely. What happens if you try to retrain the entire model? Okay. So here I'm like setting the training parameters. Image height and width will be 150 and 150. Okay, so that is actually my input size. And the train data directory is actually data/train, which is here in this location, data/train. And the testing or the validation data directory is actually the data.validation. And the number of folders within the train and validation should be same. So if you have like two classes, cat and dog in the train, and then like cat and dog in the validation, that is good. But if you have like two classes in the train and then three classes in the validation, then during the validation, your model will not actually like do it, because you have mismatch in the number of classes. Now here the model weight file is equal to like Vgg16 x for weights transfer learning. So if you want to like save this transfer learning model in case, you can use this particular name. And number of epochs is equal to 5. Number of epochs is how many times you want to run the new model in the new data set. Okay. Now we are going to use the pre-trained model for creating the new transfer learning model. So what we do, input equal to input of shape of 150 by 150 by 3. We keep 3 because this is actually a color image. So we'll be using a like input shape of 3. And the thing is like this model is also trained for the color images only. So we need to actually consider that factor also. The thing is like sometime maybe the model that you want to train is actually for grayscale images. In that case, you need to extend your dimensions of the grayscale and then make it into 3 channels. Only then the model will actually able to figure out what kind of features they want. So you cannot use a model which is trained for RGB and then directly apply for the images in the grayscale, because that will have only 1 channel. Here technically we can do, because technically the model tag can take like any kind of input size. The input size is actually not mentioned. Okay? But the depth should be 3. The depth of the model, the depth of your input should be 3. Okay. So even if you are training maybe a grayscale image, you can actually extend the dimension into 3 and then still train the model. Okay. So you try to define the input. Then what you do, the model Vgg underscore convolution will take that input, and the output of your base model will actually take it here, and whatever the output is there, you try to flatten it by using the flatten layer. So here the like this thing is already flattened, but like I mentioned, many of the neural networks, they will have a kind of like a 3D output volume, 3D activation. So in those cases, you need to flatten it. So what will happen? The 512 will remain the same. After flattening, what I'm going to do, I'm going to add a layer of 16 nodes, sorry, 64 nodes with the activation of Leru, and then the final layer with the 2 classes, 2 nodes with the activation of softmax. Now we are going to give it with softmax because the softmax is the activation function for the multi-class classification. And here the number of classes are 2 because we have cats and dogs. Okay, and this is our X. So we create the model here. Model will be like taking the input, which is the input, and the model will create the output, which is here, and whatever that is in between will be now fetched into this one. So you give a input and then you try to give a output, and whatever that is there in between will be constructed as a model to map the input to the output. Okay, and we'll do like model.compile. Compile will compile the model. Loss is categorical cross entropy. Now this is the loss function or the error function to train the model. Cross entropy. Cross entropy is actually the loss function for doing the classification. If you are doing regression, then you'll be using mean squared error as a loss function. Optimizer is RMS prop. What is the optimizer? I think you might have heard about this stochastic gradient descent or gradient descent method. The optimizer gradient descent will actually try to minimize the loss function, and they will try to update the weights and biases, and will give a good model. So RMS prop is actually the modified version of your gradient descent, which will try to update your weights and biases and finally give a trained model. And metrics is accuracy, and this metric will actually change from problem to problem. So here we are dealing with the image classification, though the metrics is actually accuracy. If you are doing with the object detection, then your metrics will be intersection over union. Okay, intersection over union means like what should have been detected and what was detected, what is the overlap between the 2 boxes, and what is the total area from the 2 boxes. Okay, and otherwise this is actually the dissimilarity, intersection divided by the union. So again, the like these kind of evaluation measures will actually change from like problem to problem. Most of the time we'll be using the accuracy as a metric for classification. Okay, so similarly for image segmentation also we'll be using this dissimilarity, dice metric. If it is a regression problem, then your metric will be mean squared error or R square score or mean absolute error or any other error metric or similarity metric. Okay, so we compile the model. Oh, image width is not defined. If you are getting this kind of error that something is not defined, you need to define it. So you need to run this particular cell. Okay, great. Now if you see the model summary, this model summary will actually show the transfer learning model. It shows that you are giving an input of 150 by 150 by 3, and then the functional Vgg model, which is the base model, will actually give a 512 activation by taking the 150 by 150 by 3. The number of parameters in that model is actually 14 million something. Okay, 14 million parameters, and after the flatten, your output is actually 8192. So here you are getting 8192 because the original model was actually taking 128 by 128 image. So if the model is taking 150 by 150, this 512 by 512 will also generate some kind of like a 3D volume of output. Okay, 8192 divided by 512, and that will be 16. So that means the convolution of this base model to this image is actually going to give 4 by 4 by 512. Okay, the 3D volume, this one will be 4 divided by, sorry, 4 by 4 by 512. So if you flatten the matrix like a 4 by 4 by 512, then it becomes 8192. And that is the exact reason why you are actually using the flatten, because the CNN model can actually take any input, because the input height and input width is actually not defined. Even the batch size is not defined. Okay. Sometimes if you try to define the input size here, then the model will have that particular input size. See, input tensor, input shape. By default, it is none, but you can give any input shape. And the default input shape is actually 224 by 224. All right. So these are like a few things that you have to take care while you are doing the transfer learning. Doing the transfer learning is not just about downloading the pre-trained model and then adding 2 layers and then training the model. It is not just like that. So there are like a lot of logical things which are going on. Okay. So now this is actually the like a brain transplant. This is the brain of some other model, and we try to fetch it here. So 8192 is actually the activation of the base model for this image. And after that, we are adding 64 nodes. So 8172 into, sorry, 8192 into 64 plus 64 biases. This is the fully connected layer. So the number of parameters are 5,24,352. Okay. And the final layer, 2 nodes, 64 into 120, sorry, 64 into 2 plus 2 biases. So that will be 130, 128 plus 2. So the total number of parameters are 15 million. The number of parameters that you can train is actually 500,000. The non-trainable parameters are actually 14. So even if you compute the activation for all these layers, you're not going to train it during the training. Okay. Yeah. So here what I'm going to do, I am going to like read the data set. So there is image data generator, which is going to like define what kind of image that you want to generate from this data set. This image data generator is actually a kind of data augmenter. You know, data augmentation. Data augmentation is like reading some data set and then trying to simulate the like different images from the same data. Because if you have few number of samples, then the model will overfit. So you try to like do kind of augmentation and replicate the number of samples so that your model will have like more number of samples to train and still don't overfit. So if you do like data augmentation, this will like try to rotate the image, try to crop the image, and all these images will have the same class name, which is the cat. And now after the augmentation, you have more number of samples to train the model. So image data generator is actually the built-in data generator from the Keras. So rescale equal to like 1 by 1 to 2 to 55 means like we want to rescale all our images into the value of 0 to 1. Shear range is equal to 0.2, zoom range is like 0.2, horizontal flip equal to true, vertical flip equal to true. These are like some of the flips. This is like horizontal flip. It is like flipped horizontally. So you can do a vertical flip also, then the cat will actually become like ulta. But usually people don't do that like vertical flip, but you can do that also. If it doesn't change the meaning of the image, you can do that. Okay, so the data augmentation is applied only for the training. We don't apply the data augmentation for the testing. So what we do, we try to apply the data augmentation for the training only. So from train dot underscore data generator, we flow from the directory. We give the directory path and then say the target size is 150 by 150. So this is going to flow from the directory and create samples with a size of 150 by 150 by 3. by doing a lot of these augmentation. Now shear range, zoom range is all like the image augmentation methods. There is a library called Image Augmenter, IMGAUG. And this is a very famous package for doing the image augmentation, where you find all these different augmentations, like all these are the augmented images. Okay, similarly, there are some packages for audio also, video also. In the audio, if your audio is there, you can actually do some kind of filtering and then make it into lady voice, gents voice, change the pitch, change the timbre, okay, change the speed, change the gender, change the like age of the audio, okay. You can do all these kind of augmentation and then simulate maybe 10 different type of audio sounds. So for them, there are other libraries for doing that, okay. So here we are like simulating the training data, and then here we are simulating the validation data, and here we are creating batch size of 4, and then class mode is categorical. So if you execute these two like data generators, it will go through the like folder and automatically finds that you have 4 images belong to 2 classes. And again for validation, you have 4 images belonging to 2 classes. Now please make sure that the number of classes are same. Number of images can be different, but number of classes should be same, okay. So now here is the way we train the model. We try to make the model checkpoint after the training. We make the like model checkpoint VGG transfer weights H5. Then we try to monitor the validation loss. If the validation loss is actually coming down, it is totally okay. If it is going up, we stop the training. Okay, that is called yearly stopping. So what we do, we compile the model. We compile the model. I think we have already compiled the model previously also, but here we like maybe compile the model again, no problem. Okay, so model dot fit generator. Usually if you have the data as a numpy file, you can use the model dot fit. Since you are going to use the data generator, you need to actually do it with the model dot fit generator. Instead of like X train and Y train, you are going to give the train data generator. And the callback is equal to callback. This is the callback for doing the model checkpoint, and epochs equal to 5. How many number of times you want to train the model? Validation data is equal to validation generator. Now let us train the model for 50 epochs. Okay, keras is actually not defined. I think I don't need this particular line because the model was already compiled. So now we are actually training the transfer learning model, which is this architecture, sorry, this architecture. And we are going to train it for 50 epochs. If you go to the runtime and then see the runtime type, you can see the GPU there. Means we are actually using the graphical processing unit to train the model. So we're doing research in the deep learning field, we actually need a GPU. I don't know why it takes too much of time. Okay, so it is like training the model accuracy is like there is like only 4 images now, so that's why the accuracy is actually like in terms of like 0.5, 0.25, 0.75, 1, 1, 1, 1, 1. Then you are like training the model for 50 epochs. Your training accuracy has become 1 because it has memorized the entire training set, and your validation accuracy is actually 0.75. It means for the unknown samples, the model is actually detecting only 3 images properly, and it cannot detect the 1 image, rest of the 1 image. Let us see whether the validation accuracy has reached the 1 at any point. Yes, it has reached 1 at some point. Since you are like overtraining the model again and again, so if you are training the model again and again overtraining, what will happen is like your validation accuracy will also come down because you are trying to fit the model more for the training. Okay, maybe if I train the model only for few iterations, I would have got the validation accuracy 1 also if I stop the training here itself. Okay. Now I think maybe the model will be somewhere here, or I'm not really sure where the model will be. Okay. All right. So let us test the model. Let us test the model with whatever we have. So here I don't think we need this line. Okay. So training is done. The validation is also done. We have done the validation along with the training. So the validation is actually very important. We try to validate whether the training is actually going properly or not. That is the purpose of the validation set. Okay. So we have a trained model, which is actually the model we have model dot summary. This is the trained model. The weights will be actually now trained. Okay. So what I'm going to do, I'm going to download an image from the internet. I'm going to download this particular image and then give to the model and see whether it is going to say whether it is a cat or dog. Okay. So I will download this particular image. It has been downloaded as an image here. And for doing the testing here, let us actually give the image path. So content, then this is the image copy path, and then give the image path. So if you want to apply the trained model and try to get the prediction from a new image, then we need to actually apply the similar pre-processing which people have done for the Vgg 16 model. So what you do, you try to load the image using the path and then convert into target size of 150 by 150, and then convert the image into an image array, and then try to apply the pre-processing input, and then the pre-process input will be given as a input for the model, because the model is actually taking the Vgg 16 as an input. So whatever the pre-processing done for the Vgg 16 will be repeated for the new images also. Okay. So we try to read the image and then try to do it, and then we apply the model, and then from there we try to get the output of the model. And if the output of the model says that if it is 1 0, it means cat. If it is 0 1, it is dog. So that is a cat image. Let us see whether it is saying cat or dog. It is saying cat. Okay. Let us download some other images. So I have seen this image. Okay, I think this is also cat. Oh, no such a file or directory. Okay. You need to give a complete path. Again, the model is saying like cat. I don't know, maybe it is saying cat all the time, or let us give one more image, which is actually a dog. So this wget command is used for downloading the image or downloading any image or data set or a zip file from the internet directly. Okay, so let me give this particular image. Oh, it is saying dog. It is saying dog. So now we can say that, okay, maybe my model is actually doing well. Maybe my transfer learning is actually doing well. This is actually the golden retriever puppy that we can actually give now this retriever puppy, golden retriever. Yeah, okay, I'm happy. I'm happy that I have like downloaded 4 images externally. 2 of them are cat, 2 of them are dog, and luckily, like they are doing really good. Okay. So the power of transfer learning is actually now demonstrated that the 4 images were correctly classified, and the model has never seen these 4 images, and somehow it is able to generalize, even though the validation accuracy is actually just 75%. It is able to classify the 3 images out of 4 images correctly. But from externally, your accuracy is actually now 100% for all the 4 images. Okay. There are few reasons why the model actually works. There are few reasons. So the reason is, if you actually take the ImageNet classes, there are 1,000 classes. And there is like a lot of cats in the dataset, and there is a lot of dogs in the dataset. And there are like, again, many animals in the dataset. Okay. So we have like a tabby cat, tiger cat, Persian cat, Siamese cat, Egyptian cat, catamount, polecat, Madagascar cat, cat bear. Catamaran is not a cat. Okay. All right. So similarly, I think there are like a lot of dogs also. I don't think like Maltese dog, some dog, Old English sheepdog, Shetland sheepdog, German Shepherd dog, mountain dog, Bernese mountain dog, French dog, Eskimo, coach dog, PUBG dog, pug dog, hyena dog, dog sled, hot dog. What the hell, hot dog? Hot dog is a food. Okay, so there are like a lot of cat images and dog images which are in the data set. Now, even though this model has only seen 4 images in the training, it is now able to generalize for the unknown samples, because the original data set contained a lot of cat images and dog images. And this has really helped the new model to do actually some generalization. Okay. So the one thing that we have to keep it in the mind is actually the similarity between our source data set and the destination data set. Let me clear this whole thing. A similarity between the source domain, we call it source domain. This is the target domain. It should be high. It should be really high. So just imagine that you are actually taking a model which is actually trained for the ImageNet, and you are going to use that model maybe satellite image classification. I don't think that the model which is trained for the ImageNet, which is going to perform really well for the satellite image classification, because there is no similarity. None of the classes in the ImageNet has like something to deal with the satellite images. None of them. Okay. But if it is about a general domain, if it is about a general domain of like cat, dog, and then types of dog, types of cat, type of cars, then this is going to surely help to transfer learn. Okay. So similarly, if you want to do medical image classification, if you are doing a totally a different domain, you are giving a MRI scan or maybe the like X-ray, then the model will have not any idea like what the image is all about, because the general domain doesn't really look like your target domain. Okay. So you need to consider this factor also, that whether your source domain and your target domain has some similarity. Okay. So that is something like, you know how to write code in Java, you are good in the Python language. Being good at the Python language or Java language is not going to help you to learn South Indian languages like Tamil, Telugu, Malayalam. It will never help you because the language, the programming language is different, the human language is different. Okay. But if you know Hindi, it is easy to learn Marathi, Gujarati because there is a similarity. I'll tell you one more thing that the people from South India, they find it very difficult to actually learn this Sanskrit based language, all the like northern Indian languages like Rajasthani, Bhojpuri, Hindi, Haryanvi, Punjabi, Gujarati, Marathi. All these are actually having a similar vocabulary, similar structure. So there is some kind of similarity. So they can easily learn the other's language easily because there is like some similarity and the transfer learning can be very, very easy. And people in the south, the language like category is totally different. This is actually a problem in the NLP. You know, like if you want to develop a Gujarati NLP, you can actually use the Hindi NLP. That is what I'm saying. I'm not like dealing with the race, religion, culture, all these like taboo things, but I'm just saying in the general. So if you have like some vocabulary in the Tamil that can be used in the Malayalam also because some of the words are very common. And the South Indian languages, they are from like a single umbrella called Dravidian languages. So they have some similarity. Since these two different classes of like languages, they have like a very high difference. It is very hard to learn. Like for me, I'm from South and I've been here like for the last 3 years. I can understand, but I cannot like speak a fluent Hindi. I mean, it's my personal thing also. I did not like put too much effort in learning the language. But here I was like comfortable with like many people. They are very friendly and English friendly. So the thing is like it's very hard if the similarity is like very low. Okay, so that is what I'm saying. And if the similarity is very low, then you try to train the model from the scratch. I cannot use my like linguistic skills in the Tamil to actually learn the language of Hindi because there is no similarity. The structure is different, the like grammar is different, and the word structure, everything is different. So that's why we try to actually do a transfer learning if there is a similarity. And you have to decide whether to actually use the base model with the weights or just use the base model architecture. You know, sometimes we can actually train the model by just keeping the base model without any weights. You know, sometimes people just take the architecture. If I say like weights equal to none, what will happen is like the weight will be actually random weights. I am going to use only the random weights. Okay, you can decide whether to use that brain as a fresh brain or whether to use the brain with some weights. Okay, not all the transfer learnings are actually going to help you, and please remember that also. You need to like actually approach the whole stuff with the whole CNN in the mind, whether the CNN has learned something related to your new domain or not. Okay, so please choose all these things wisely. Sometimes people just try to like take the architecture only by keeping like weights equal to none. So maybe we can do that experiment now. We can do something like this one. We try to keep the model base model without any weights. Means only the architecture is there. So it is just a skeleton without the weights. What I'm going to do, I'm going to freeze the, no man, I don't need to freeze. I need to like actually train the whole model. I should be like training the whole model. So let me try to give the whole model. So I should not freeze now. Okay, I think these are all here. So let me create a model. And now the entire model can be trained. Yes, all the parameters can be trained. Okay. And data set is prepared. We can just take that architecture, VGG architecture. We can train the model from the scratch. So the model is actually giving 50-50 accuracy. I think this is, from my view, like the model is not actually learning anything. I think it is just giving a random input, random output. So it is not really training anything. Maybe I think there is a problem with the learning rate or something. The models, because there is a 4 images, and if you say that all the images are actually cat, if you say all the images are cats, then what will happen? You'll be accurately like doing the classification 50%. Your accuracy will be 50%. Okay. So out of the binary classification, if you say that all the images are cats, you are absolutely right, 50%. Your accuracy will be 50%. Okay. So I think there is a problem with the model in starting the training. So initially the validation loss is like a very high, loss is very high, even though the loss is actually coming down a little bit. It is like stagnant after some time. It is not even improving. Okay. So there is an option that we can actually train a model from scratch like this also, like taking an image and then like adding a convolution layer, doing a max pooling, convolution, max pooling, drop out, flatten 32 dense layers. So this is a model, like a custom model, which is going to be trained from the scratch. Okay. And here I think we need to import the keras. Only then the keras.optimizers will work. Okay. So if I try to train the model from the scratch, it is giving accuracy of 1. Again, it is fluctuating. That's a problem. If you try to like, yeah. So after some time, you are getting like accuracy of 1 for the training. Validation, you have like 75%. Okay, just like before. The model.summary is here. This is the custom model, not a pre-trained model. Custom model. Okay, so let's see like how the model is giving accuracy. It is saying cat, but it is actually a dog. It is again saying cat, but this is a dog. This is a puppy. And it is again saying cat, it is a cat. I think the model is like giving like cat only for like every image. The model is like biased towards the cat class. Okay, that's a problem here. Okay. So this is what actually going to happen if you try to train the model from scratch, because the model is actually training with the lesser number of samples, and the training accuracy may be high, but testing accuracy will be very, very poor. Okay. It is very easy to memorize the entire data set of 4 images using a trained model from the scratch, but it is very hard to generalize. That generalization will actually come only through this kind of like transfer learning. Okay. All right. So let me try to give you one more notebook where we try to do the transfer learning with some other data set. Okay. This is cat and dog. Let me try to give it some other thing. So I think this notebook also I will share it with you after the session. So please share. So let me connect it. I think there are too many sessions, so I need to kill this notebook. After saving it, I can kill it. Okay, so let's reconnect. So in this particular data, this particular notebook, what we are going to do, we are going to do the transfer learning with the flowers data set. So this is a particular like a domain specific data set. And the number of classes will be like 5: daisy, dandelion, roses, sunflowers, and tulips. So the main difference between the flowers will be the color. Okay, so this is going to be the data set from the Kaggle for flower classification. So these are the number of images. And this is like the number of classes. 242 images of flowers. Sorry. All right. So what we do, we try to like import all these basic functionalities. But the thing is, like, if you are trying to look for transfer learning code, the internet will have like a lot of different varieties of code. The code will not be simple like we have seen. Sometimes the code will be having like many more complex functions and like user-defined functions. So it won't be like in the similar structure. So whatever the structure is, you should be able to connect like what is actually happening inside. Okay. So sometimes you need to learn the like particular notebook or the code on the way, and you cannot memorize this code. You have to get like what is the gist of it. So let me give a like a quick overview about how we can actually understand the code which is written by the others and simultaneously try to running it. So here I'm assuming that I'm just like putting my mind into your like head. I'm just like trying to behave like you. So I think there is like packages, OS, and then system, and then math. I think these are useful. NumPy is there, matplotlib is there for plotting. TensorFlow as TF. This is the TensorFlow package, and we are trying to like print the TensorFlow version. And auto is equal to tf.data.experimental.autotune. Okay, so there is something. So we try to import all the packages, and the TensorFlow version is 2.5. And the thing is, like the TensorFlow already has all these like images, flower recognition images as a TensorFlow record files. Okay, so this is already there locally within the TensorFlow. So there is like a GS colon flowers public TF records hyphen JPEG hyphen 192 by 192 hyphen 2. So in this particular folder, all the images are actually available as a TF record. TF record is something which is similar to the H5 file for storing the data set or storing the model. Okay. So image size is 192 by 192. Batch size is actually 64. Batch size is actually the number of samples we are going to process per batch. And they are saying like 128 works on GPU, but comes very close to the memory limit of the Collab GPU. So if you increase the number of images in the batch size, then the GPU will also be occupied with a lot of images, because simultaneously you want to run the 64 images at the same time. So if your size of the image is very high and the batch size is very high, sometimes it will actually throw this error called out of memory error from the CUDA. CUDA is actually the backend for your model. And the solution will be like reduce the batch size until your code runs without the error, or reduces the size of the model until the code. Even in the morning also, I received one of the like out of memory error from somebody in my research group. So they were saying that we are getting out of error. And I found that the same GPU is actually used by some other people. If you get out of memory error, maybe it is used by some other people, or maybe the model is too big to fit into the single GPU. Every GPU has a capability of like 16 GB or 4 GB, and your model memory should be fitting into that. Validation split equal to 0.19 means like if you want to have a 19% of validation set. Classes is actually given here. So file names, GCS pattern, I think like automatically this will give the file names of your TF records. And here from the file name, you try to split it. Splitting will be done by this percentage of images, like 19% of images, whatever the number will come up to the training. After that, it is for validation. So again, you are calculating the steps, how many number of steps you are going to do. So that is also calculated here. So don't need to worry too much. This is just a setting of the size of your training samples and the size of your testing samples, how many steps, and then how many steps for batch. Okay, we don't need to worry too much. So here we are writing the function for reading the TF record. So whatever the like record, TF record is given inside, we'll be trying to like parse it into a single example. From the single example, we have image and we have class. So we try to extract both. So the TF record contains like image also, the class also. So return, you are trying to like return the image array and the class labels. Okay, so the load data set will actually call all the TF records. Okay, so I think here they will be using that read.tf record, and along with that you are going to give the file names for the TF record. And here it will take the file names, and the file names will actually come from here. So the file names will be given to the load dataset, and the load dataset will try to read all the TF records, and the TF records will read the images and the class label and then return to the original position. That will become your dataset, and that you get it from here. Okay, so this is like the innermost function, and this is the outermost function. Okay, and you try to read it. Display 9 images with the prediction. This is going to like help you to just display the images. Okay, just a 3x3 grid, and you try to plot the image with the label. Okay, all right. So here we are trying to like get the batched data set. A data set is actually a full data set. We try to like divide into like batches. Okay, so that is what happening in the whole code. And please don't worry like how they are doing it. This particular code will change from time to time. Maybe after some time, maybe after 2 years, the code will become outdated. So one thing is actually pretty standard. That is actually the whole procedure, how you are doing the things. That whole procedure will never change. You need to import the library. You need to import the data set. You need to like convert into batches, and sometime you need to do some augmentation, and you need to define the model structure, and you need to compile the model, train the model. Okay. So process, one of your microphone is on, I think. So please. Okay. Okay. So this is the procedure. The procedure will never change. The class will never change. The way we do it, the language, how we do it, that will change. If you take the same code in the PyTorch, then the things will be totally different. Okay. So that's why it's very hard to keep up with the code of deep learning, because every year it will change, and it will rapidly change. And we have to like be ready for this kind of things. Frankly, when I see any code the first time, I don't really worry whether the code is actually like understandable or not. I just read the function name and try to understand that, okay, maybe it is trying to get the entire data set and then converting into batch data set. So only the batch data set with like batches of samples can be used for training. Okay, that is what I understand. So we try to run this thing. Now it is trying to read the entire whole like data set converted into batches. Okay, so let me see what is actually the trained data set. What is the type of it? Okay, it is actually a kind of prefetch data set. It is of own type. It is containing like 193 by 193 by none. I think this will be generated on the way. You know, you cannot like see the samples within, but this will be generated on the way. Okay, fine. It's totally fine. Data set to numpy util. So I think the data set is actually in a different format. So from the data set you can get the batch, that is a data set, and from the data set you can actually get the images and the labels, and from the numpy images you can get the numpy array, and the numpy labels you can get the numpy labels. Okay, you know, it's very simple as it is. Title from label to target. Okay, So this is the label and this is the correct label. And it is trying to say like the label should be something, otherwise it should be something. Okay, so this is to like just convert the label into like the target label. So from label to target. So I will tell you the reason why we are doing it. So we try to do the one-hot encoding. I hope that you all know the one-hot encoding. One-hot encoding is actually a procedure to convert any categorical input into a binary value. Okay. So here the data set is actually a discrete value. And in your model, you want to have something like activation 0, 0, 0, 0, 1 for tulip. For daisy, you want like 1, 0, 0, 0, 0. So the number of nodes in the last layer will be actually 5, and one of the node will be getting activated, and the target will be also a binary number, and that will be something like this. So if you have like 4 unique values in your pet, then your 4 columns will be there, and cat will be represented as 1, 0, 0. This is called one-hot encoding. One is hot, others are cold. Okay. So I think here I am trying to do one-hot encoding. Okay, so one-hot encoding is there. Display one flower is actually for displaying a single flower image using the plot. So you try to get the image and then the title and then the subplot. We try to like put the image I am show with the title. So all these are like very simple. Display 9 images from the dataset. Again, this is like given a dataset, it will display the 9 images. Okay. Display 9 images with the prediction. It will display the 9 images with the prediction. Display the training curves. If you give the training and the validation curves, I mean the values for like epoch 1, epoch 2, epoch 3 and all, it will try to plot it as a like diagram. So let me try to display the 9 images from the dataset. Just a funny, this is a code written by somebody else. Okay, I have not written it. So this is like 9 images. So these are like daisies, daisy close up, daisy like far away, daisy black and white, like a daisy. This is also daisy. I think this is like all the class names of the images, types of the image. I think, no, dandelion. Okay, so these are the dandelion. I think maybe there is a mistake here. This should be dandelion, and this should be sunflower. I think somewhere like display 9 images from the dataset, and then display number to util, get the 9 images. I think somewhere there is a mistake in the name of the dataset, name of the label. The title is like class equal to np.argmax of label of I, and image is there, label is there. Okay, I think here there is a mistake. All right, fine, but we are focused on actually the transfer learning part. So now again, just like what we have seen in the Keras model, again from the TensorFlow we are again importing the Keras package. From the application we are importing the Vgg, sorry, MobileNet V2. MobileNet V2 is actually the again a pre-trained model. Again you are trying to like get the input shape equal to image size of something, and you can say that weights equal to ImageNet. You can download it with the weights of ImageNet dataset. Include top equal to false. Include top equals false is very, very important, because we don't want a last layer. We actually want one layer before that. So you can directly set the entire model also, say that pre-trained model dot trainable equal to false, the entire model will be frozen. The whole pre-trained model will be frozen. So let me try to break this entire thing into 2 parts and try to tell you what is actually happening here. Okay, so we try to download the model, and we have like a pre-trained model dot summary. Okay, that is here. So this is a VGG, sorry, MobileNet V2. MobileNet model is actually very famous for deploying the model in mobile phones. All right, here So here we are actually putting something like model equal to sequential of pre-trained model. From there we try to do flattening, and then we are adding a dense layer, and this becomes a model. Now this is your transfer learning model. If you want to add more layers, you can add more layers. You can add like one more TensorFlow dense with like ReLU as activation or sigmoid as activation. You can do anything. So you try to construct a sequential model by putting the base model. On top of that, there is a flatten layer. On top of that, we have a class with the 5 layers. Okay. So now if you try to like execute it and then get the model.summary, you can see that the number of non-trainable parameters are 2 million, and that is exactly equal to the base model, which is actually there, right? And rest of the like 230 trainable parameters are actually from the last layer. And you know, the funny thing is like, let's say that you have these many number of nodes, and you are connecting with maybe an intermediate layer of maybe 512. What will happen? If you just try to connect like this one multiplied by the 512, then the number of parameters will actually increase. Like this is 92,035 lakh 23 million. Okay, so this is actually 23 million. Just a single layer will contain 23 million. Okay, so it is really not preferred to have a larger value here. You are getting a larger value here because your last layer is like that. 6 into 6 into 1280. Okay. So sometimes maybe instead of flattening, you might want to add one more convolution layer, reduce this again further, and then try to reduce into a smaller one so that this number will be a smaller number. Imagine that again you are dealing with like a 512 number of classes. Then this is going to like blow your entire model. So instead of that, maybe you can do something like tf dot keras dot layers dot con. Let me put con 2d. Yes, con 2d. I can say that this can be like a 3 by 3. I can put like maybe just a 32. This one 32 filters. Okay, I think there should be a comma here. Yes. Nice. See, what I have done is like instead of flattening this particular base model, I have just added a convolution layer and reduced the dimension into further 4 by 4 by 32. I have specifically given this number 32 because you are going to get a small output in the flatten layer. Okay, so if you have a plan of having a like large flatten layer, I mean like a large dense layer, then the parameters of your model will actually blow. It will like blow double or triple. In this case, it will blow like 10 times because your base model is just 2 million and your model will become like 23 million. The new layer that you add. The new layer, the single layer should not be like really this much big because it is more likely to actually overfit. Okay. So it is totally okay if you have something like 512 in the previous layer and you add like 512 here. So 512 by 512 will be like a much more smaller number than these million numbers. Okay, so that is just 2 lakh, 0.2 million. Okay, so again 100 times smaller than the 23 million. What I have done, I have just added a convolution layer. So we have to be like very careful. The transfer learning is not just about like taking the base model, then flattening it, then trying to add the layer. It is not just like doing things blindly. We have to be like little bit like careful. Okay. So the number of nodes in the last layer will be 5, and then the activation is softmax. So here I can give the activation also. The flatten is just a flattening. Okay. The thing about the convolution neural network is actually your like height and width of your convolution output will be small, but your depth of your convolution will be really large. You know, That is actually the one of the challenges in the CNN. There is no control over the depth of your CNN. So let's say that we are dealing with the AlexNet model architecture. In the AlexNet architecture, you can see that height and width of your images keep on coming down. See, like 227 by 227, 55 by 55, 27 by 27, 13 by 13. But your depth is keep on increasing because the number of filters you are keep on increasing. And since the depth is keep on increasing, like Mr. Alex got really careful, and he tried to reduce the depth into 384 into 256, so that this number becomes small. If you try to deal with like a 13 by 13 by 384, or just say like 6 by 6 by 384, this number will become very large. Let me tell you how. 6 by 6 by 384, it will become like 13,000. 13,000 if you try to connect with the 4,096. So 13,000 multiplied by 4,096. Man, this is like really big. 56 million. We don't want a 56 million just for a single layer. Okay. We try to reduce this number so that you have some freedom in the last two layers. So for that, you need to do any kind of strategies to reduce the number. So that reducing the number is nothing but reducing the number of filters in your network. I have done it by just adding the 32 nodes. Again, if I am stupid and saying like 512, then what will happen? Again, this will become a big number. Again, if I try to connect this 8192 with the 512, then there is no difference, right? So I need to reduce it. I should not reduce it too much low because it will lose the essence of your activation. I cannot keep it too high because that will increase the number of parameters. Okay. So all these things are like really matters when you actually do the transfer learning. So there is no like a global standard or like a global formula. This is how you have to do the transfer learning. Whatever that works for you, whatever that is like feasible in terms of smaller memory and better speed, we are okay with that. Okay, so fitting is very easy. You just put like a model.fit train data set that will contain the whole thing. Okay, so that will be having like steps per epoch, then epochs equal to something 5 or 10. Yeah, 10. Validation data is there, validation step is there, and then let's run the model for the training. So this data set is a little bit like bigger data set. It has like 4,284 images. So this is going to take some time. Cannot be trained in a fraction of a second like we have done in the cat versus dog. I think this is going to take some time. I'm really not sure like how much time it is going to take, but let me open
Sir, can we
yes, sir.
Sridhar sir, can we start the question answer session?
Yeah, sir. I'm opening the discussion. Yeah. Anybody who has any doubt, please let me know. I think the
Sri Lakshmi,
yeah.
Your hand is raised. You can ask.
So side by side, you can just keep a look at this particular output also. After like maybe the first epoch, second epoch, we are reaching the accuracy of 98, 99. And you have to keep an eye on this validation accuracy also. It should be increasing side by side. Okay, so please go ahead.
Good afternoon, sir.
Good afternoon, madam.
This is Sridhar, sir. Sir, in the previous example, when you are training for the dogs and cats,
Yeah, madam.
the data sets.
Yeah.
When you are downloading the dog image,
yeah,
last but one before the golden dog.
Yeah, madam.
There in the prediction, the output given as 4,1, and the output as dog. Generally, our output should be 0 or 1 because 0 will be the cat and 1 will be the.
Oh, okay. I think like there was one sample where you have seen like a fraction number, no? Like 4 points.
Yes, 4 point something.
Yeah. So that was like 4 point something into 10 power minus 32 or something. That is a numerical problem, madam. With the Python, sometimes it happens. Sometimes we'll have a activation like 0.9999, and then the other activation will be like 1 into e power minus 32.
Yes, sir.
Yeah, like you are right, madam. So we want actually a binary output or a probabilitical output.
Okay, sir.
So we try to do argmax. Argmax means we try to take the maximum index out of the output array and then try to take that label from that.
Okay.
Yeah, great. Any other doubts, please let me know. See, like accuracy is 99.93, really nice. Doubts, please?
Yes, Krishna.
Sir, can you suggest some books where we can start from scratch for the transfer learning?
Hello, am I audible, sir?
Yes, yes.
Sir, actually, I wanted to ask you that I'm looking for one publication regarding in this area. So, sir, can you just suggest me some of the journal name where I can publish my work related to your area only, sir?
Sorry, my teams got. Yeah, professors, please.
Krishna, ma'am, you can ask. I think some network issue.
Okay, okay.
Sir, actually, I want to ask that I want a suggestion regarding one journal in which I can publish my research paper.
Okay, madam. Yeah, please ask. Yes, professor, please go ahead.
Krishna ma'am, please repeat your question.
The question was like journal.
Krishna, ma'am, go ahead.
Yes, sir. I am asking about journal name in which I can
Journal name,
publish
like,
my
okay.
paper, and yes, sir.
So journals, like my personal opinion, will be like. So when we actually do research, we try to read the papers, and we try to get some good papers from top publishers, Springer, and then like Elsevier, IEEE, ACM. These are like top layers. So sometimes you find a paper, or if you find like set of papers from the same journal. For some problems, this like same journal will be publishing like the same kind of problem. For example, object detection, that will be published in a similar kind of journal. More papers you will find it in the same journal, and that will increase like they are interested in those kind of problems. Okay, that is one thing. And most of the time I try to go with the LCVA journals because they have like quick turnaround time. And some IEEE journals also I used to publish it in the letters. Letters will be like just 4 pages. So in the LCVR also there are some 4-page letters, like 6-page letters. There are like short journals which are like they're very famous. And I have not tried like any transaction or anything. And that's my suggestion. Please go with like SEI index journals and free journals. When I was doing research, the only like hope we have for the publication was the code, releasing of the code. Okay, so we try to release the code and then we try to prove ourselves. Then the reviewers are convinced. So that also is a very important thing. If you are doing in the deep learning,
Anjali, ma'am, you can ask. Anjali, Naik. Go ahead, Anjali, ma'am.
So sorry again. I am not really sure like why it is keep on crashing. My apologies. So some journals are there like for deep learning. Some journals are there for like machine learning. I personally publish in pattern recognition.
Sir,
Use
I want to ask you, if can you suggest me uh, understanding for the basic code or deciding how the lines should be added for adding the filters or adding the layer, one more convolution layer if I want to add. So all these basic things, just by uh, uh, for writing go into deep or designing your own model, it is important to understand. So how do I go about it?
Okay, so if
Basic
you are like trying to
creation of the
publish a
code.
paper, if you are trying to like do some novelty in the like research, there
Yeah.
are two things that we have to keep in mind. That so we try to imagine that what are all the things which are accepted as a novel contribution, but we have to be very sure that what are all the things which are not accepted as a contribution. So if you are like working with the deep learning and you are saying that I am going to apply this model for a new problem, that is not a contribution. So you cannot say that I have applied this Vgg model for a new data set, and that cannot
Right,
be a
sir.
contribution. It is a contribution, but not a really big contribution for accepting the paper. And if you are adding a
Sir,
layer and saying that I have changed activation and then I have changed architecture and it is giving a better accuracy, that is also not a contribution. Doing a modification is not a contribution. Or maybe adding more data and then saying that I have better accuracy, that is also not a contribution. Then the question is like, what is the contribution? So you need to actually find a failure case from the previous model, that the model may be failing in some cases and you need to give a reason why it fails. And to solve that failure case, you try to do some modification in the network. For example, maybe the model is actually failing to detect the cats which are in the like maybe in the better lighting or like a poor lighting. The lighting condition of the image is very bad, and the model is very sensitive to that. So you tell that this is the failure case, and I'm going to like give a solution for that. And to give a solution, you are going to propose something within the pre-processing or maybe in the model architecture. And sometimes you do some modification and then try to solve these failure cases, and eventually you will have a totally new model which is going to solve the problem. And the change that you have done to the original model is actually the contribution part. And we have to actually go something like, I have done this because I want to solve this. It cannot be something like I have done this and then this is giving a better result. Just accuracy or the speed of the model.
Sir, thank you very much for your information. I want to ask uh, if you suggest me some reference from where I can learn writing these small lines of making little modification in the code. So for that basic understanding of writing the designing a model,
Okay.
so instructions are important to understand. So from where I can study that?
So a lot of resources are already there in the like internet, in the GitHub. There are a lot of tutorials. So I cannot like name a single what we call single source of all
So
these people.
which one you found most useful to come to this stage?
I'll tell you,
Such
madam.
a
I try to Google search.
experience.
Okay, so if it is transfer learning with the CNN, I'll try to do Google search. Transfer learning CNN model. Then IPyNB, .IPyNB. If you keep it, then all the Python notebooks will be there. Then I open it. I try to run it. If it is running fine, then I try to understand the model. Most of the time, what happens is like half of the code doesn't really run in the Collab because maybe they are outdated or maybe they are like not properly written and they have done some modification and you don't know what they have done. So I try to get the running code and then try to understand it. And sometimes I like run a code and then I don't understand the code, whole code, even though code is actually running. If I don't understand the code after the first two or like three different glances, then I don't follow that code. I just throw it away. So there is something like readability. We start with like very simple programs which are like straightforward. People have written a lot of commands and tutorials, and then you try to move on to like the notebooks which are written by the researchers, where they are actually the implementation of the papers. I mean, these days the problem is actually there are too many resources and we don't know what one to read. So
Yes,
that's
that is
actually
the
the
problem. That is
problem.
why I
Yeah.
am asking you if you suggest me exactly some documents from where I can start, make my start.
you just search something like that, madam. Simple tutorial for CNN, simple tutorial for Keras. Then people used to write blogs about it, like in the medium towards data science, in the analytics vidya. Then we have like a lot of different blogs are available, and there people used to give a lot of instruction. For each and every line, they used to write a lot of things. So you try to read blogs for writing the code because they give like a lot of instruction.
Okay, sir. Okay, thank you so much.
Yeah, I think before I leave, I just want to like introduce a small thing. Today is like a very good day for me because I have submitted like course in the Udemy and then it got published today. Okay, and this course is actually for moving from machine learning to deep learning. So today it got published. Thank you, madam. So I try to keep the price minimal. The current price is actually 1,280, but it will come down after some time. Today it got published. Just morning I received the message. So most of the time we are
Sir, okay, maybe there is some network glitch.
It's a network issue.
Sir, can you share his mail ID?
Yes, sure. Through WhatsApp, we will share the mail ID of Sridhar Swaminathan.
I'm really sorry. Again, there was a problem in my system, I think.
No worries, sir. Everyone has learned a lot from you, so I think they can little they can
Yeah, madam.
tolerate this much. Okay, sir. Allow us to thank you for the today's session. Thank you, sir, for the wonderful hands-on session. As hands-on session always increase confidence to use techniques. Now, I hope participants have learned and practiced as well hands-on session along the session, and this will help them in their research work. Thank you once again, sir.
Thank you, madam, and thanks to the.
And a very big
team.
congratulations, sir, for your Udemy course.
Thank you so
Hope we
much.
will also enroll someday and learn few more things from
Yeah.
that course. Okay.
Thank you, Sridhar sir. Thank you.
Thank you, sir.
And
Thanks to all the
congratulations.
participants also. Thank you, sir. Thank you so much.